look at some problems where we actually use the equilibrium constant associated with acids and the equilibrium constant associated with base, Ka or Kb, or pKa and pKa, another way of representing that. So, or Kb, or pKa, or pKb. And again, these are just ways of representing Ka or Kb. Let's take a look at a problem. If the pH of a 0.100 molar nitrous acid solution is 2.125, determine the pKa. So we have this nitrous acid solution, and we are asked to determine the pKa. So, well, what we really need to do is actually determine the Ka. And so before we get there, though, we're going to need to know the form of the equilibrium constant. Acids and bases are equilibrium. Acid and base problems are equilibrium problems. If I'm asking you for a Ka, what I'm really using is the same basic idea of calculation. Determine the equilibrium constant. And so the way we do that, we have products over the reactants, HNO2 plus water in equilibrium with NO2 minus plus H3O plus to give us NO2 minus H3O plus all over HNO2. And this is undissociated HNO2 at equilibrium. We're told that initially you start with 0.100 molar HNO2 and you allow it to come to equilibrium to generate a solution that has a certain pH. Well, here, that's gold right there, pH, H2O4. Well, that is related to the H3O plus concentration. 10 to the negative 2.125 will equal H3O plus. And so we can calculate this. And it says that the H3O plus concentration is equal to 7.498 times 10 to the negative third molar H3O plus. Where did that come from? Well, that came from the forward reaction of this HNO2 plus water going to NO2 minus. All of that H3O plus came from the decomposition of this. That means that the implied bit of information is that this is also the amount of NO2 minus. Every single one of these had to be made at the same time as H3O plus, because we start with just nothing but HNO2 in solution. So all we have in solution, it has to fall apart to make the NO2. So we now know that the concentration of the NO2 minus is equal to 7.498 times 10 to the minus third. Means that one's taken care of. We know that one's taken care of. And we even know that this initial concentration, that whatever has decomposed, will give us the HNO2 at equilibrium. Now, once we do that, once we do calculate that value, we could actually do two things here. We could calculate it, or let's try and say, well, okay, let's pretend that we use the weak acid assumption. The weak acid assumption says that at equilibrium, the HNO2 concentration will be approximately equal to what you started with, because HNO2 minus X will be small. And so we can plug this value in, and see how that works. Well, let's take a look. Let's compare these two values. This is 1 times 10 to the minus 1. This is 7 times 10 to the minus 3rd. That looks like it's pretty close. We might be able to get away with it. Now, if these numbers were, if this concentration was much higher, we might run into difficulty. But we can try it. Plug those values in. If we had done the subtraction, if we had not used this assumption, instead we were to plug in those values and measure the concentration, you'd get 6.07 times 10 to the minus 4th, which is close enough for government work in this case. So we used to get very comparable values without the assumption. Again, you can use the weak acid assumption as long as you're dealing with about 3 orders of magnitude difference, thereabouts. It gets a little more iffy when they get closer, and this one is right on the borderline. That's a typical problem. pH is code for H3O plus information. Here you have phenoxide. Phenoxide is a weak base, pKb of 4.0. And they say, what is the pH of a 0.33 molar phenoxide solution? So you have an initial concentration, initial solution value is 0.333 molar. What is the pH of a 0.33 molar of phenoxide? Now, what is phenoxide? Who cares? All right. Because they tell us that phenoxide is a weak base. So even if we don't know anything else about phenoxide, somehow when we put that base in solution, that phenoxide base in solution, that it will react with water to release hydroxide ion and pick up a proton. In reality, phenoxide is an aromatic compound that has a negative charge on it, and usually we'd use sodium phenoxide or something along those lines. And in the presence of water, it forms phenol, picks up the proton from the water to make the OH minus. The proton is transferred from the water to the phenoxide. Now, again, we don't really need to know that because it's a weak base. A weak base, and they give us a new solution. If they give you a pKa or a pKb, they give you a Ka or a pKa, treat it like a weak acid. Start your calculations like they're weak acid calculations. They give you pKb, you might want to use the weak base equilibrium to be more effective. Kb of this compound will equal the base concentration, OH minus, divided by protonated form, all over the weak base at equilibrium. They tell us that initially the concentration would be equal to 0.333 molar. That's not enough to solve the problem. We also need Kb, but they don't give us Kb, they give us pKb. But lucky for us, we know that 10 to the negative pKb will equal to Kb. And so we know that this is equal to 10 Kb equals 10 to the negative 4th for that compound. So we can set this equal to 10 to the negative 4th. And through the beauty of the chemistry, we know that for every one of these that decomposes, for every whatever this initial amount is minus whatever is and through the beauty of chemistry, we know that whatever the initial amount of this that decomposes produces one of the hydroxide and one of the BH plus, and we can plug those all into our equilibrium statement to obtain a value of X, the hydroxide ion concentration, if we rearrange and solve. But because this is a weak base, we can use that assumption 0.33 molar minus X is approximately equal to 0.33 molar and plug that value in and rearrange and solve. 5.77 times 10 to the negative third. Yay! All right. Except no. We're not done yet. The question asks us, what is the pH? Well, that was the hydroxide ion concentration, and through the magic of what we learned last class, get a pH equal to 11.761. That's the answer.